those two functions share? Just structurally, what's the similarity between the two? Y equals, right there. The structural similarity, which I just drew a little too much of, the structural similarity is the Y equals right there. The Y equals right there. That's the structural similarity. What's nice is that they are in that form, which we've kind of assumed is the only form, Y equals. So, how could they also be written? Well, you could have an implicit function. These are a little different. Can someone tell me what structurally is different about this one? What's structurally different? What? Y is not isolated. This is an implicit. Y is not isolated. So your first tendency, if I asked you to work with this function, if I asked you to do anything with this, and be careful with the word function right now, but if I asked you to work with this, what might you want to do right now? What might you want to try to do? Yeah.
Isolate.
You might want to try to isolate Y. We're not going to do that right now. We're not going to isolate Y. And there's a good reason for that, and we're going to get to that shortly, but we're not going to isolate Y. Let's say I asked you to graph this thing. If I asked you to graph this thing without isolating Y, just graphing it, what's the default way you can always go about graphing something? What's the default way you can always graph something? You can always make a what? Sarah?
Oh.
What could you always make? What could you always make? Yeah. You could always make a table. You could plot points, right?
Yeah.
You could plot points. So you pick x values and you find the y value. You pick x values and you find the y value. So if we made a chart right now with x value and a y value, what are some good x values that we could use?
0.
How about 0 is one of them, right? What else?
2.
We could use 1 and 2, and maybe -1 and 2. Fill that in for me, everybody. Fill in that chart around the origin. Oh, that's nice. So we just graphed it, but here's the thing. There's an upper part and a bottom part. Is that a function? By the definition that you've had before. Is that a function?
No.
Why not?
It just
Doesn't pass the vertical line test. So implicit functions can double back on themselves. So we graphed it. I could ask you B now, and this is where we have to be really careful. I could say find the slope at x equals 1 in two different ways. There are two places, though, where x equals 1. X equals 1 right here, and x equals 1 right there. There's two places where x equals 1. So the first place x equals 1 is right here. We know what that point is. What is that point? That's 1 comma root 3. And what's this point right here? Right there. Similar, what is it? 1 comma negative root 3. And are there other points that are kind of like that? There's -1, negative root 3, etc. So if I just gave you this picture without a function, if I just gave you that picture without a function and I said, estimate the slope of the tangent line, what would you draw first? Draw the what? Draw the tangent line, and then you can estimate the slope. So what can you tell me about this slope? Is it going to be positive or negative? It's going to be negative, maybe like -1/2 or something like that. And what about this one? Positive half, probably, right? But we'd like to be able to do that algebraically. We'd like to be able to do that algebraically. When I first showed you x squared plus y squared equals 4, what did you want to do to that first? Maggie, you said it. What did you want to do to that first to work with it? You want to isolate the y. So you're over here, and let's do that first. We had x squared plus y squared is equal to 4. What could we subtract from both sides? X squared. So we have y squared is equal to 4 minus x squared. And then what do we do to both sides right now? Take the square root of both sides. So what is it going to be? Y is equal to the square root of 4 minus. What has to go out front of that square root? When you take, plus or minus. So there are actually two functions here. And there should be, because what do you have up here? You have the top arc, and then what do you have below? The bottom arc. Which one do you think the blue one is? That's y equals the positive square root of 4 minus x squared. And what's the green one? The negative, exactly. So let's say I wanted to find, everybody, let's say I wanted to find the exact slope at that top one. Which function do I use? I use the blue function because the blue function is the top one. So if I want to do the slope at x equals 1 for the top one, we use the positive one. So let's use the blue one. So it's y is equal to the square root of 4 minus x squared. If I want to take the derivative of that, what do I do with the square root? What do I turn that into? Square root is what power? Sarah? A half. So we have y is equal to 4 minus x squared to the So now we take the derivative of this. Can someone tell me what the derivative of that is? Someone raise their hand who hasn't spoken. Liv, go.
Y equals 1/2 4.
1/2 times 4 minus x squared to the what power?
-1.
Half times what?
2x.
Close.
Negative.
Negative 2x. So if I want the slope where x equals 1, what do I plug in for x? 1. So y prime at 1 is going to be 1/2 times 4 minus 1 squared to the negative 1/2 times negative 2x. What cancels? There's something that cancels nicely there. What cancels? That cancels right there, right? Oh, what do I put in for 1 there? I'm sorry, that's just a 2, right? Yeah. So what do you end up with? Y prime at 1 is going to be 4 minus 1 squared to the negative 1/2. What does negative 1/2 mean for power? What does negative 1/2 mean for power? So it's the square root of what? What's 4 minus 1 squared? 3. You put it in the denominator, right, Liv? So what is this going to be?
1 over.
It's going to be negative 1 over the square root of. See the negative that was there? So did we, oh, is that about what we thought it was going to be? We were looking at the slope and we thought, was it going to be positive or negative? We thought it was going to be around negative 1/2, right? What did we find the slope to be actually? The slope was negative 1 over root 3. So if we wanted to do the green one, what function would we have to start with if we wanted to do the green one? Y equals what? Negative 4 minus x squared to the negative, to the half, not negative 1/2. X squared to the 1/2. Do we do almost the same work? Do we do almost the same work? Yeah. You're going to end up with y prime is equal to negative 1/2, 4 minus x squared to the negative 1/2 times, oh, does something cancel here? What cancels here? Well, that cancels with that, right? So we do y prime at 1. What do we end up with? 4 minus 1 squared to the negative 1/2 times 1. What's 4 minus 1 squared? 3. So what do you end up with? 1 over. Oh, is that about what we thought it would be? Yeah, it's the same thing but going positive. Is it always going to be a mirror? No, it's not always. But in this case it is because it's a, what's the shape of this? Okay. Is that a decent amount of work right there? It is. But it was predicated on the fact that we could isolate y. This right here was kind of nice, right? It made us feel nice because we could do something with a form that we've looked at before. Here's the thing. Can you always isolate y? What do you think? No. I can change little tiny things about it like this. Can you isolate y on that one? Y cubed minus xy equals negative 6? Just say no. It is possible, but it's really hard. It's really hard. So here's the thing. Sometimes you can isolate y and sometimes you can't. So what we're going to do is we're going to do it the second way, which is called implicit differentiation, where we're going to start with this, but what are we not going to do first? We're not going to isolate y and see what happens. And here's how you do it. Let's say we couldn't isolate y, we were stuck. Y is some function of x, but we don't know what it is. Y is some function of x, but we don't know what it is. So what I'm going to do is I'm going to say y is equal to some function of x, and I'm going to write it like that. X squared plus f of x squared is equal to 4. We don't know what function it is, but we're going to write y equals f of x just for notation purposes. I like doing this notation. It's helpful. We're now going to differentiate. So the first step was let y equal f of x, and then differentiate with respect to x. So if we differentiate with respect to x, what's the derivative of x squared? 2x. Now be very careful here. What's the derivative of f of x squared? We don't know what f of x is. Careful. What do you think it is?
2 f of x.
To the what power?
To the 1.
To the 1 power, right? Times what?
Times f prime x.
Times f prime x. Why did you make it times f prime?
Because chain rule.
Ah, because of the chain rule. Exactly. And what's the derivative of 4, everybody? This is the most common mistake. 0. People do this all the time. They write the derivative of 4 as like 1 or 4. It messes up the entire thing. So do we have to write that first power in there? No. What do you think we want to isolate right now? What do you think step 3 is? not the f of x. Isolate f prime. We want to know what the derivative is. But here's the thing. What was our original substitution, Liv? Y is equal to what? F of x. So what could we do right now if we wanted to? We could change it back. You could change it back. You can change it back at any point. I like changing it back now because notation helps. I like the notation this way, everybody. So if we change it back, what do we have here? 2x plus 2y, y prime is equal to what? 0. What are we isolating? Same thing. We're isolating y prime. What can we divide everything by? No, divide by 2. Divide by 2 and you get x plus y prime is equal to 0. So what does y prime equal? Negative x, not y1, y prime equals negative x. So what does y prime equal? Negative x over y. So we just found the derivative of this function is what? What's in the derivative that usually isn't in the derivative? It needs to be there now because when x was 1 on this circle, how many points could you be at? 2. You could be at multiple points. So to isolate a point, you need an x value and a y value. So actually, is this correct? F of x? The way you'd actually write that is f of what? You could write it like this to be totally perfect. You could write it like that because what's going into the function? X and y. So let's go back and look at our circle here, everybody. What were the two slopes of those two tangent lines? Can you see them up there? I'll highlight them. They're here and here. You see the two slopes? What was our derivative? We found the derivative. Do you remember what it was? Our derivative was, so we knew f prime, we can say f prime of xy if we want to, was equal to negative x over y, right? What's the point here? 1 root 3, right? Oh. Negative 1 over root 3. What's the point here? 1 over negative root 3. Oh, is that a lot easier? Yeah, it's a lot easier. Especially since sometimes you just can't isolate y, like full stop. That cubic thing, y cubed, the next one we're going to look at, you need a cubic equation. Do you remember what the quadratic equation is? Yeah. Negative b plus or minus the square root of b squared. You can use that, right? Is there a cubic equation? Mm-hmm. Is it really nasty? Is there a 4th power one? Yeah, there is. There's one for everyone except 7, which is an interesting story. But they're really nasty. What's a lot easier? Implicit differentiation. Yes, Sarah?
Can we apply that rule to all points? Or
Yes. Correct. So now you could find the derivative, you could find the slope at any point you want, but you need the x and y coordinate. So for example, what's the tangent line at x equals negative 2? Well, what's the coordinate? Negative 2, 0. But negative 2 over 0 is undefined, right? That's a vertical line. Yeah, it works, see? It works. Okay, so let's go look at this one. Hey, can you isolate y? No, you really can't. You really can't. So do you even try to isolate y on this one? No. Say no. Really, just say no. Say no. Okay. What was the first step? What did I tell you to do first? Let y equals f of x. And the reason I do that is I want you to remember the chain rule. It's really easy to forget the chain rule. So the first thing we're going to do is say y equals f of x. So what do we end up with? F of x cubed minus x times f of x equals negative 6. Now, what's our next step? Do you remember what it was called? Differentiate with respect to x. So can someone tell me what the derivative is going to be? Be really careful. Maggie, go.
2.
Careful. It's a 3.
Sorry,
3 f of x to the
second
times
f prime
f prime
of x.
of x. And then what do you have to use right here?
Product.
Yeah, the derivative of the first times the second plus the first times the derivative of the second. And then what was that third step that I said, what could you do at this point to make things easier for you?
Change it back.
You could change it back. I like that step. Sometimes you can change it back at the end, but I would say change it back. Change back. So what is that going to mean if you change this back? What's it going to turn into? It's just a lot easier to write. 3 times y squared y prime minus y plus xy prime. Do you see the parentheses I'm putting in? Are they really important to have? Yeah. Look, everything is the same. There's f of x. There's x. There it is.
I feel like it's easier to write it like that.
It is much easier to write it. The reason I want you to do this is it's really easy to forget the chain rule. It's really easy. When you do this a lot, like in the next week, you won't have to do the whole y equals f of x thing. You can just do it if you remember it, but you need to remember that f prime. When you do the derivative here, it's really common for people to forget that negative 6. What's the derivative? It's 0. The second most common mistake, what rule did we have to use right here? What rule is this? We use the product rule. What do people forget to do? The product rule. They just say the derivative of xy is y. Is that true? No, you have to use the product rule. I have found, especially at the beginning, if you make this substitution, it forces you to remember the chain rule and the product rule. Because x times f of x, you have to use the product rule. What do we isolate now? What do we isolate? We isolate y prime. So we have to distribute first. We have 3y squared y prime minus y minus xy prime equals 0. What do we add to both sides? We add y, yeah. What do we do now if we want to isolate y prime? What do we do now? What do we do now if we want to isolate y prime? Begins with an F? Factor. Y prime times what? Equals y. And hey, do we have an answer now? Y prime is equal to what? Y over. Hey, did you just find the derivative? You did. You just found the derivative. Fantastic.
Oh no, I wanted to like think first.
Okay. How about this? Take a wild guess. Just take what see if you can write down what the derivative is in terms of t. Just write it down. What do you think you do with that third power? What do you do? Yeah, so it's going to be negative 9 times x of t to the what power? But what do you multiply by now? X prime of t, right? We don't know what that is. It's x prime of t. Minus what? 4 times y of t to the first power times what? Y prime of t equals what? Equals 0. Now, what's any? You can answer this. What's another way to write x prime of t?
dy dt.
Careful, it's actually dx dt. And what's this one going to be?
dy
dt. So here's the thing. We are going to do problems where there are two rates of change that change with respect to time. In this case, is there anything to isolate now? Say no. There's nothing to isolate. Because are these the same derivative?
No.
One's dx dt and one's dy dt. We're not isolating it yet, right? You'll be able to plug in everywhere else. We're not isolating it. The only thing I want you to take away from this problem is, can you differentiate with respect to time? Absolutely. The kinds of questions we're going to be doing are things like, if I'm watching a rocket go up, like how fast is the angle measure changing at a certain time, right? Because the angle measure slows down a little bit, or like a shadow is increasing in length, or someone's running around a track. Like if you're running around a track and it's a circle, like how fast is the person moving in like that direction at a specific time? The topic is called related rates. We will be doing the next over like 4 periods. It takes a while. But the first thing you have to do is the mechanics. So what I'd like you to do right now is you can start your homework.